Thank you, and good morning, everyone. It's a pleasure to be here, so I want to first thank the organizers for inviting a Gaia presentation at this occasion. And I can tell you that it's also a pleasure to me, after several years of talking about the potential of Gaia having the launch date ahead, and now having the launch date behind, having Gaia at L2 and working, it gives much more freedom to speak what I'm going to speak now. So first, in one slide, summarizing everything what you really should remember of Gaia. So it's the ESA billion star surveyor, and it's really building on a heritage in Europe to do astrometry. This was started with Hipparchus, and what Gaia is doing, it's just learning the lessons from Hipparchus and doing things orders of magnitude better concerning the sample size, accuracy, and also expanding it to spectroscopy. So what Gaia really is all about is astrometry. That's the thing, what you have to go to space. You cannot do it from the ground. And that's the core of the mission, to get the astrometry done right. But in order to do astrometry right, you have to do also photometry. When you go to high precision, you have to also know the colors of the stars in order to do all the corrections. And if you do photometry, you can actually do photometry for science. So of course the photometry in Gaia it's like a mission of its own, a full sky survey, or photometric survey of the sky. And one of the lessons really learned from Hipparchus is that if you say that you can do spectroscopy from the ground, so don't do it from the space. It's true, but at the moment, of the 120,000 Hipparchus stars, about half have radial velocities. So if you don't do it at the same time, you will actually never do it, and especially with the sample sizes of Gaia. So it's a complete package of providing astrometry, photometry, and spectroscopy. Now, one of the things to note of Gaia is that it's a satellite which is built by industry. There is no PI institutes building instruments, and this was considered to be more useful because of the system aspect of the whole mission. You have to consider everything from payload to service module to do it properly. So it is done by Airbus Defence and Space. ESA is doing the overall management and operations, and where the scientists are coming into the play are in the data reduction. So this, of course, has an intrinsic problem that the people who have to work with the data, they actually haven't worked with the hardware. They are decoupled. So one of the things what we really have to take care of is that the people who are reducing the data understand what they are doing. And I think that now in the commissioning, we have really seen when this collaboration has been worked between industry, ESA, and the data processing consortium, that people in the data consortium are well aware of what is happening, and they have a true contribution for the commissioning activities, and you can go with the confidence into operations because you know that the people are already aware of how everything works in Gaia. So I mentioned already we had the launch last year with Soyuz from Kourou. I was hoping to give you here an end result of the commissioning. However, we are still right in the middle of it. We are expecting to finish by middle of next month. After that, we will have the nominal 5-year mission, Gaia operating at L2. And in the intrinsic for astrometry doing parallaxes is that you need some patience before the data comes out. So current estimate of the first data releases are mid-16, which will be positions and proper motions to Hipparchus stars. And the real parallaxes for stars, you have to wait half a year, roughly more. And if you want to really keep up to date, and especially when the commissioning data is coming, it's the place to look is our website. Just very quickly, what Gaia is all about. 2 telescopes. You need 2 telescopes for doing wide field astrometry. Everything silicon carbide, not only the mirrors, but also the optical bends. 1 focal plane, so you get stars from 2 directions mixed on the focal plane. And silicon carbide for the extreme thermal stability we need to have. And in reality, it looks like a torus kind of structure, which accidentally, or not so accidentally, has the same size as the Herschel mirror, because it had to be baked in the same oven to make one unity out of it. Mirrors are rectangular, and we truly have 2 of those ones. And the focal plane is a huge area covered by 106 CCDs, And the basic principles of observing is that Gaia doesn't know anything of the sky in advance. So there are first sky mappers mapping everything what is on the sky in order to decide which are the objects we want to measure more precisely. And the sky mapper CCDs are the only ones which know from which telescope the light is coming. So they also have the bookkeeping task. They have to then remember which star came from where. Then in the astrometric field, we are just collecting and following the stars which are bright enough for Gaia. And for those ones, we also do photometry. We do spectrophotometry in 2 parts, blue and red. And for a fraction of the stars which are bright enough, we do also spectroscopy. And they also have to pass the focal plane of those places where we have the spectrometer CCDs. Pixels are not square. That's a peculiarity. That's matching that we have in the scanning direction the high resolution. So we match the pixel sizes to that one. Also the mirrors are matched to that reality. And one of the things to remember is that we are using a TDI mode to read the CCDs. So we are spinning all the time, and in order to keep sharp images, we have to read the CCDs exactly with the same speed as we are spinning. And when we have all the CCDs on the focal plane, 106, this one is now flying with Gaia. I will not go too much into the science details, just a few comments. A couple of first bullets are about the structure and dynamics of our galaxy. This is really the key science driver of Gaia. This is putting the requirements for the whole mission. And then when you have those requirements on the table, you actually realize that you can do much more. And of course, stellar astrophysics is really the people who are really looking for the distances. If I make a talk to professional astronomers and say that what we are doing are distances, you have the audience at your side, because everyone knows how hard it is. It's totally opposite when you have an audience of general public. If you say that we are looking distances to stars, you always get comment back, didn't you know it? But with professionals, it's somewhat easier. So we do galactic structure people make happy with Gaia, stellar people. With exoplanets, Gaia has a unique slot what Gaia can do. We will be very good in detecting giant planets, not close to the star, but more like the Jupiter kind of orbit. So if we think that the solar systems, which have a giant planet at far away orbit, is interesting, Gaia will find those ones. For solar system, we get the asteroid orbits more accurately than anything on the ground, so you can do all the dynamical groups and look into new categories of objects. We get 500,000 quasars, so we can combine the optical reference frame to the radio reference frame. And of course, because there are so many stars around, if you have that reference frame, wherever what you are looking in the future, you will find some stars where the positions you know very accurately. So all telescopes in the future, all satellites which are having star trackers, they will all use Gaia catalog to point the devices. And finally, just to mention that we are also doing fundamental physics. What we have already decided to do, we are having a scanning law, but to the initial conditions of the scanning law, we have tuned in such a way that 2017, when a bright star happens to go close to Jupiter, we are looking to get the quadruple moment of the gravitational effect of that occasion. So it's really the breadth of science, galactic structure, even reference frames, quasars, fundamental physics, stellar physics. That's why Gaia has such a wide support among scientists. And I just want to show one field related to science more. It's Bardes window, and I think it illustrates the problem what people are facing. You can probably, from this picture, see bright stars. You can guess they are close to our sun. You see 2 globular clusters. You can guess they are very far away. But the rest, there is the 6 kiloparsec arm, there is the 3 kiloparsec arm, and there is also the bar around our galactic bulge. But the only way to know that, how many stars are where, how they are moving, is that you measure them. You measure the distances, and you measure how they are moving. And that's what we are going to do. Now, back to the status of the spacecraft. This is just a few months before the launch. Gaia came in 2 pieces into Kourou. The spacecraft and the sun shield were separate, and they were assembled together at Kourou, and here it's the fitting to the launch interface. We had a frigate, which is the fourth stage launch capability for the Gaia, was already from the previous satellite, which had a delay. So we took that frigate, put Gaia on top of it, and then the combination of Gaia and frigate was put into the nose module. And at the left-hand side, you see the last hole in the nose module. Our quality assurance person was the last one to look into the window and tick the box in. Gaia is inside the fairing. And then we had a real rocket. I mean, not something what you see in reality, but something what you remember from comics books when you have been as a child. Soyuz looks really like that. The Soyuz in Kourou, it's transported from the assembly line to the launch pad horizontally, then it is erected, and then only the nose module is put on top of it. So that's the difference to the Baikonur launch. And we had the launch 19th of December, and there were just some clouds, and we could beautifully follow Gaia, what is happening. The whole week, it was low clouds and raining, and you could see absolutely nothing, a misery. There was only one exception. It was the 19th of December, and thanks to that, we could follow Gaia for several minutes when it was disappearing into the space. And the next day, it was raining again. And just in one day, it's far away, and it's just a streak what some amateur astronomers have been able to find. Gaia is already on its way to L2. So what did we do at the early phases? We had the automatic sequence. We got the transmitter working, gyroscopes. Payload had a double connection. It has a flight connection and also a ground connection. And with pivots and the ground connection we had to release so that there is no thermal contact. The chemical propulsion system was primed, and thermal control was configured, sort of standard activities after launch. We got the sun acquisition, we deployed the sun shield, and we started the payload decontamination. And then there was just preparations for the day 2 maneuver just before Christmas, and that was all executed successfully. So everything went at the beginning very quickly. We had the focal plane switch on 3rd of January. We had the final burns 7th and 14th of January to go to L2. And all maneuvers and all the launch, everything has gone actually really very precisely, which means that we have lots of propellant in case we need for additional maneuvers. So the propellant budget is looking very healthy. And early January already we started the 6-hour spin, and in so-called ecliptic pole scanning mode. Gaia is scanning the full sky in the nominal mode, combining 3 motions: spin to get the great circles, and then with L2 going around the sun in 1 year. And on top of that, we are precessing the spin axis in order to get the full coverage of the sky. So for the early phases, we actually fixed the precession. We fixed the spin axis to ecliptic plane, and that ensures that we can always observe the ecliptic poles. And that helps because we have prepared the ecliptic poles stellar catalogs for calibration purposes. So we are using this specific scanning law at the beginning of the mission. And very soon we got the first light. Before anything was aligned or focused, we just took a shot to a very bright star, which saturated actually. But you can see from the double peaks and the form that we are not in focus. The focusing has been, the telescope alignment, the focusing has been a long iterative process, which took quite some time. But at the moment, we are really having optimum focus, and telescopes are aligned. We have no issues there. And the focus is good for the whole focal plane, so not only for the astrometry, but also for the spectroscopy, for the spectral resolution. I mentioned already that we are using the TDI mode, so we have to spin exactly the same speed as we are reading the CCDs. So when it's an iterative process where you are focusing and then you are adjusting the spin rate, because both have to be fine. So this is the illustration of just an extended object, which we could take Left hand is when we are not with optimum spin rate, and right hand side is when the spin rate has been tuned. There's been several iterations after this one, but then you cannot see anymore with the bare eye that the image is improving. You have to then look for other measures to convince you that that's happening. And then when we were reasonably focused, we took a little bit harder target to Gaia, a star cluster in a Large Magellanic Cloud, just a small field, about 200 by 200 arcsecond. And just again, to a little bit illustrate the potential of Gaia, so this one is 2.8 seconds of integration time, and this corresponds to something like 1% of the astrometric field of view. So if you then think that, of course, when we observe with 100% of the field, and we don't observe 2 seconds, we observe 5 years, you can get the feeling of how much data Gaia is going to provide. And just a comparison that indeed you need to go to space to get the high resolution. Essentially what Gaia is observing, it's not quite the Hubble Space Telescope spatial resolution, but very close to that one. And then just a few images to convince ourselves that everything is working. It's just dumping down some images at the moment when something interesting is passing by. And here you see also one of the effects of Gaia. We are scanning, and if an object happens to be between 2 CCDs, then it's a black area where you don't see anything. We are not pointing Gaia to anything. We are just scanning the sky as it passes by. And just finally showing one image of M51, again, just a very short integration to show that we are capturing also extended structures. I think this will be for the ESA outreach people a big surprise when soon we will take no images at all anymore, and it will be all just point sources. And you can imagine the disappointment, because that will be very difficult to sell to the general public, while for astronomers we will not really have that problem. Then a busy field of Gaia, just somewhere in the galactic plane. So the first thing what here is still to note is that actually, even a busy field, most of the sky is empty. So it doesn't really make sense to send all this empty data down. So what we are doing, we are identifying the stars. So this is the real measurement. These are the objects what Gaia onboard software has identified on the fly. And these are all assigned a window, and they are sent down. It might be difficult to see, but here are symbols. Some are squares and some are circles. The square ones are something what we are using also to control the attitude of the spacecraft. And I will mention something more on that one in this one. What we are doing with the attitude control, we do it with the micropropulsion system. So the chemical propulsion is for the big maneuvers. The micropropulsion is to keep Gaia stable, doing exactly the spin as we wish. And there is a loop that we are looking all the time on the payload, how the stars are passing by, and with that speed, we are correcting the spin. And what you see in the plot is there is a deviation of the spin rate in units of milliarcsecond per second after a micrometeorite hit. So what is happening, first Gaia is spinning fine, then the meteorite hits Gaia, you get the speed change, and within few tenths of seconds, we have been seeing enough stars on the focal plane. They have gone to the computer, and the computer has calculated what kind of thrust to give with the micropropulsion system, and we get few micronewton thrusts, and we correct and bounce back. This is a little bit bigger hit, so we overcorrect first, but within few minutes, we have recovered completely from the hit of the meteorite. So micropropulsion works, and also their healthy budgets. We have cold gas for possibly 10-year mission if everything works that long. Phased array antenna, we have no moving parts, so we have it array which is electrically steered beams, because we are spinning with 45-degree angle to Earth, so we have to change all the time the beam without moving anything. Also very healthy budget, we can get all the data down, we can use high rates. We have a rubidium atomic clock that is working properly. We need good clocking, because that's in a way our coordinate calculation. All 106 CCDs are working, all the back-end electronics are working, data acquisition is working, and everything goes to the memory. We had to also change at some point the scanning line. We got much more data than anticipated, and that sort of unintentionally we could also prove that the data deletion in a priority order on board is working properly, so low priority stuff gets written over high priority stuff if needed. Photometry, it is spectrophotometry, and this is kind of data what Gaia is going to give. So very low resolution spectral energy distribution. This is the red part, and it's ordered by the temperature of the stars. So you can see that in red part, the cool stars are dominating, while if you look the same thing at the blue part, then you have the hot stars, which are relatively stronger in the spectra. Everything looks like nominal, like simulated, so we expect to have at 15th magnitude stellar temperatures to 200 Kelvin, metallicities to 0.2 dex, gravities to 0.2. So it's of course not, as for individual star, a very good thing, but what you have to again remember, we do this for tens and tens of millions of stars. And finally, the radial velocity spectrometer also working. So we have Gaia's spectrum at top of a very bright star, and a ground-based spectrum which has been then convolved to the Gaia resolution, just to prove that we see all the lines what we should see on the Gaia spectrum. And the radial velocities are template fitting. So what we fit, we have a model of the star, and we match which radial velocity matches best the observed Gaia spectrum. Just as a coming back to spectrum again, or the quantities, we have been doing commissioning and all kind of measurements, and every now and then doing the nominal scanning law. What we have already gathered by this moment, we have about 1.5 billion spectra in the database. Now, not everything is going fine, so we have issues which we have to deal with. We have much more stray light than anticipated, and we have identified some of them come from Milky Way and zodiacal light, but there is clearly also an element which actually also disturbs most coming from the sun. We have not been able actually to identify. We know it's the sun, but how it enters, even now that we see where it enters, we cannot deduce how it happens. But it is the fact, and it impacts the faint sources, and especially the spectroscopy. Another thing where we have to be spending, that's why our commissioning is still ongoing. We have been exploring the stray light issue and also the transmission loss, is that we see that as time, a function of time, the transmission is going down. So we are having somewhere a source of water, and we get some frost on the mirrors. It's not too worrying because we have heaters, so we can get rid of it, but it is sort of annoying that we have to do this heating operation more often than we thought. What we are observing is that the rate we get frost is diminishing, so there is less water. However, the water is not exhausted. And finally, one of the key things of the astrometry is that we know exactly what is the angle between the two telescopes, because that's the global solution for astrometry. And we anticipated this angle to vary, and that's why we have a specific device on board, basic angle monitor, to measure these changes in the basic angle. Now, the measurement, the equipment is working really fine. We have the precision needed for the Gaia accuracies. The only thing is that the amplitude is larger than what we thought in advance. So what we are going to do, with stray light, we are a little bit stuck, so we have new manpower, fresh minds looking into if they can identify what the paths are. And also parallel, we are modifying the onboard software when we are going to a different domain that the background is more significant than anticipated. So there we will recover some of the lost sensitivity. For the contamination, we have a procedure, and we have to do it now. And we probably have to do it later this year, and maybe even after that. This is something also to monitor. So it is an annoying thing that we lose 1 day of heating and then maybe a few days, a week to cool down. And for the basic angle, we are still conducting specific measurements just to get the confidence that the measurement is precisely as anticipated. And we do this by changing the focus a little bit, and then we know what kind of change it should induce to the basic angle. Now, if we just now stop all the activities and put Gaia running and observing, so these are the estimates what we get for, I just take one example, unreddened solar type star. So for the bright ones, we are at still at below 10 microsecond parallax error, 4 millimagnitude integrated photometric error, and the spectroscopic radial velocities at 1 kilometer per second. At 15 magnitude, 25 microsecond error in parallaxes, a little bit poorer photometry, and there we are then hitting the sort of practical limit of radial velocity accuracies. And at 20th magnitude, our parallax accuracies are at 430 microsecond, and photometric accuracies, depending on the red or blue part, 60 to 80 millimagnitude. So still the accuracy at, especially the astrometry accuracy at 20th magnitude is better than what you can do in the future with LSST, or roughly of the same thing, same level. So there is still a little bit space what we are considering to go slightly deeper, because there is still mileage. We can do something unique, even maybe 20.5 magnitude to get the parallaxes, which you cannot ever get from the ground. So that's still under consideration. So what do we have to still do before 18th of July when we have the commissioning review? We have to look these limits of magnitude limits for astrometry and photometry. They are tied together. When you do astrometry, you do also photometry. It turns out that for the bright end, the bright limit is 6 magnitude, but we have now methods to go at least to the 3rd magnitude, and most likely all the way down to the brightest stars. Not with the same accuracy as this from 6 to 12 magnitude, but if you get 100 microsecond parallax accuracies for the brightest stars, I think it's worth doing as well. And at the faint end, as I mentioned already, we might go a little bit deeper than 20th magnitude, maybe 20.5. For the spectroscopy, really the activity is now on the software changes on board, and in order to fix then what is the limit, how deep we are going to go in spectroscopy, and the current guess is that we are somewhere around 16th magnitude. We do the basic angle monitor verification, that we get convinced that we are measuring the right thing. We have to do one decontamination activity before we start the nominal phase, and after doing this maneuver with the basic angle monitor experiment and decontamination, we have to have yet another round of checking for the focus. But after these activities are done, we are ready to start the routine phase. And we start the routine phase again, going to this ecliptic pole scanning law before moving into the nominal scanning law for 5 years. And as I mentioned already, we anticipate first catalog something like mid-2016. So I will just finish by saying that, with pleasure, that we have a mission. It is an L2, it is working, and I'm convinced that it will change astronomy totally, and we will see that 2016. And thank you for your attention.